guys, we're about to get started. Thank you for coming. Just real quick, oh hey guys, real quick, is everyone in here from Dr. Caldwell's class? Anyone from Dr. Dubé or anything? All right, cool. So we have like just about the one section here. That's cool. So to get started, I'm going to be working on this review. This is where you will find it, ucfstudyunion.wordpress.com. So it's different than the other review I had posted. I apologize for that if you had already printed that, but this is the one we're going to be going over. As far as the other one goes, if you did print that and already start going over that, I'm going to post the answers to that one as well, so that you guys don't feel like you don't know if you got them right or wrong. So as far as this goes, this is the review we're going to start with. It's about 10 pages long. And yeah, so just so you know, this session is going to be streamed. So you can go back and rewatch it later on YouTube. Probably either by tonight or tomorrow, it'll actually be up if you're not watching it already. So yeah, that's about all. Does anyone have any questions about anything before we start? Can anyone hear me okay? Yeah, what's up? What's that? So go to ucfstudyunion.wordpress.com. So it's not the UCFSI website. It's the UCF study. Yeah, we just have to post them to a different site for the study union. It's more centralized, I guess. But yeah. Any other questions before we start?
This is bottom C, correct?
This is what?
CD. CD.
Yeah.
Oh.
Cape Florida. Yeah.
Florida CD.
Yeah, it is. All right, cool. So, I mean, if there's no more questions, we can just about get started. All right, so let me know if at any point I'm writing outside of this really tiny field of vision given by this projector, so I'm probably going to do it a lot, so just let me know so that I can fix it. But otherwise, let's go ahead and get started. It's going to go in chronological order from the very first stuff to the last stuff. So yeah, let's go ahead and get started. So real quick to get started with the very first question. So draw the following vectors on a coordinate grid. So this is the kind of stuff we did maybe first week of class. So first thing you want to do is just draw your coordinate grid. And just so that we all don't get tripped up by something like this on the test, I just got 3 vectors to draw with different wordings on how to draw them. So 30 meters per second at 45 degrees south of east. So 45 degrees south of east. So you want to go east and then south of east. So it's going to be in this quadrant, and it's going to be 30 meters per second. So just draw, you know, they don't have to be up to scale, 30 meters per second. And we call that vector A, since it's question A. So that can be vector A, and it's 45 degrees south of east, so that we're all clear on that. And then the next one, B, is 15 meters per second, 20 degrees west of north. So notice that sometimes it'll be west of north, sometimes it'll be north of west, and they'll mean different things. So just make sure you start appropriately. So west of north, so you go north and then west, and it's 20 degrees that way, and it's 15 meters per second. So it'd be 20 degrees right here, and that's 15 meters per second, or vector B. And then vector C is the easiest one, 60 meters per second north. So this is mostly about understanding that that's the longest one. So 60 meters per second, or vector C. So does anyone have any questions about how we drew any of those? Feel free to ask questions at any point throughout. I'm happy to answer any questions. So, all right, this space is really small. So add vectors A and B from above. So now we're going to add up vectors A and B. So this right here, you might see a question like this. Essentially, all you have to remember is to add up 2 vectors, you have to add up their individual x and y components first, right? So to get started, the best way I like to do it is so number 1, we want to write our vector A has an x component and it has a y component, right? So you want to go ahead and separate them this way. And we know that vector B has an x and a y component. So we're just adding vectors A and B. So if we were adding C as well, notice that vector C just has the y component. So that one wouldn't have an x component, for example. So then to write them out, what you'd want to do is, let's look at vector A. You want to connect it to the axis, so that makes a right triangle. Do we all see how that's a right triangle? And so in this case, this would be the x component right here. So ax, and this would be the y component. And so ax would be equal to 30 cosine of 45. Any questions on how I just got that? Because I know we've been using essentially this method like the entire semester, but if anyone has any questions, feel free to ask. And then the y component would be negative 30 sine of 45. And notice I did negative because it goes in the down direction, right? So it's negative y direction. The reason why you want to write that is because when you're adding them, when you get to the point where you're adding their y components of b and a, you're going to subtract the y component of a because it's going down, right? So you want to make sure you note that. So if we found those. Ax is 30 cosine of 45. Y is 30 sine of 45. And then vector b, you just want to do the same thing. Oh, and if anyone's confused ever on how, where you're supposed to like connect it to the coordinate grid, because notice this one I connected it to the y-axis, but this one I connected it to the x-axis. It's because that's where your angle is. You just want to connect it wherever your angle is. Because if I wanted, I could technically connect vector b to the x-axis like this. I would just have to make sure I use the right angle over here. You just have to find the complementary angle. But that's just extra steps. It's really unnecessary. So then we know we have bx right here and by right here. And so in this case, by is adjacent to the angle. So that would be 15 cosine of 20. And then, so 15 cosine 20, and that makes the x 15 sine 20, but it's going in what direction? Left or right? Left, yeah, so it's negative. So then we end up with, oh, and I didn't even write the negative right here. So that's why the vectors get tricky. You want to make sure you keep up with the signs. So right there, I didn't even write the negative as I was writing it. So it's negative 30 sine 45, and the bx is negative. So you have two negative components as a whole. So now that you have all your component vectors, what you'd want to do, so step 2, is use your vector addition formula. So r, which is your resultant vector, right, equals square root of, in this case, ax plus bx squared plus ay plus by squared. So you're adding the x components and squaring that, and then you're adding the y components and squaring that. And that can go, if you're adding 3 vectors, it would be ax plus bx plus cx, and etc. And that just comes from the Pythagorean theorem, essentially. And so then you'd actually want to go ahead and plug those in. So once you plug all these in, just for the sake of time, you get ax plus bx is 16.08. So you get 16.08 squared, and then ay plus by is negative 7.1 squared. So the reason I write it that way is because, as you see, our y component, when you add ay and by, you get a negative number, right? So think of it this way. This is your x component, and this is your y component of your new vector. So that means that your new vector is going to go 16 to the right and negative 7 downwards. So it's going to be in this quadrant, the 4th quadrant. So that's just a thing if it asks you what direction it's going to be going in. So then we get r equals 17.6 meters per second. So that's the size of the vector, right? And yeah, if it was just asking to add them, it's 17.6 going in this direction in the 4th quadrant. So any questions about that one? Yeah. Oh, you got it? All right, cool. So any other questions about the vector addition? I feel like one vector addition problem is enough to go back and study it. So we don't need to do several of those. So if anyone doesn't have any questions, we can move on. Yeah.
How do we know if it's in the 4th quadrant?
Oh, good question. So right here we added our x components, ax plus bx, right? Mm-hmm. And here we added our y components. So this right here is our x component. Mm-hmm. That means that if I were to draw a new coordinate grid, like that, that means that my new vector is going to be, oh yeah, here we go. It's going to be 16.08 meters per second in the x direction. So it's positive, so it's going to be that much to the x direction, and then negative 7.1 in the y direction, so down. So my vector would look something like that. Does that make sense? Positive x, negative y leads you to that quadrant. And then I'll label that r for resultant vector. All right, so any other questions? Hello. So moving on to just number 3. Oh, hey guys, just to tell you guys, we're going over the review. I updated it on the UCF Study Union WordPress site. If you guys, I believe I linked it in my own WordPress site for the UCFSI website. So go ahead and try to follow this one along. If you were using the other one, I also will post the answers to that one. So, all right, moving on. A car traveling to the right goes from 25 meters per second to 8 meters per second in a span of 2 seconds. What is the acceleration? So this calls for that acceleration formula, which is, does anyone know it off the top of their heads? Awesome, delta V over delta T. And so this one is really just testing your directions. Make sure you know what delta is. So delta means final minus initial. So you want to do 8 minus 25. A lot of people will just want to do 25 minus 8 because you'll get a positive number. But you want to write final minus initial so that you get your answer in whatever direction it needs to be in. Your time is 2 seconds, so it's 2 seconds. And so you get negative 17 over 2, which gives you negative 8.5 meters per second squared. And so being able to appropriately write the delta is going to give you your negative acceleration. So it's letting you know that the car's traveling to the right, but the acceleration is pointing to the left, so it's slowing down. That's why it went from 25 to 8 meters per second. So any questions about that one? Nobody? Cool. All right, so I'll give you guys a second. Also, let me know if I'm going too fast at any point. I am going to post the full answers anyway, regardless of how much we get through. So I want to make sure we go at a nice pace that we all feel comfortable with. I don't want to just try to rush it to finish it. So moving on to the next one. All right, so number 4. And this one's just, as a reminder, the slope of a displacement versus time curve. So remember those curves, displacement versus time, velocity versus time, acceleration versus time. So the slope of displacement versus time is the what? Okay, good, velocity. So that right there, and then this, it goes in the same way for, because once you get the velocity versus time curve, the slope of that is the acceleration. So that's kind of the relationship they have. So the reason I input this question is so that you guys don't forget about these curves. So just in case he throws one at you, don't feel like you haven't seen that in months. Try to go back to that as well. So you throw a tennis ball up in the air. What is its acceleration at the very highest point that it reaches? Who knows? What is it? All right, got C. Cool. Good job. So a lot of people will put 0, but what is 0 at its highest point? Good. Awesome. So the velocity would be 0 at the highest point. All right, you draw. So now back to the kinematics stuff. Any questions before I start number 6? Cool. So you drop a ball from a 45-meter cliff. How fast is it traveling right before hitting the ground? Notice there's no mass involved, because I know as we moved on throughout the semester, we start to use mass for a lot of things. So for this kind of thing, the mass is not even involved. So you drop a ball from a 45-meter cliff. How fast is it traveling before hitting the ground? So you know that your cliff is 45 meters. So you know delta y equals, in this case, your final, I just want to write this out for the sake of our future questions. So delta y means final minus initial. So the final is 0 meters minus initial, which is 45 meters, which gives you negative 45 meters. So you do get a negative displacement because it's going downwards, right? You know your acceleration in the y direction equals, what is it? Yeah, negative 9.8. So, because as we move along as well in the semester, you just use g, which is 9.8. So just remember that distinction. We always use negative 9.8 for acceleration. And so we know that our initial velocity, since we're dropping it, is 0. So that's one of those things that is assumed you guys will infer from the question. So that gives you 3 things already, and we need to use those 3 variables to find our final velocity in the y direction, right? So that's a question mark. Looks like a 2. There we go. So we're looking for that. And so in that case, you would want to use one of your kinematic formulas. So this is going to be our first one we use. In my opinion, as we move, all the problems we've done throughout the semester, this might be the most used kinematics formula based on just all the problems we've done. So Vf squared equals Vo squared plus 2a delta y. So just as a quick reminder, this functions both in the x and the y. So you can do this for things in the x direction, or you can do it for things in the y direction. You can't mix variables. So if it makes it clear, I'll make 2a in the y direction, Voy, and Vfy. Remember, keep things in the same direction or in the same axis. And so we're looking for Vf y squared. So Vf y squared equals 0 squared, since our initial is just 0, plus 2 times negative 9.8 times negative 45. So remember how we got a negative displacement? That's kind of, this is how that comes into play here, because the negatives cancel out, and then when you go to take the square root of it, you don't have to take the square root of a negative number, which if you've ever had to do, it might make you question whether you did the question right or wrong. So it's just those little things like that that make you more sure in yourself, and you get 29.7. So keep in mind, I do just get the answers beforehand to write them out for the sake of time. Feel free to check me on all of them, because I have been known to be like terrible using a calculator. So just check my math at any point if you guys feel like that's wrong. So how fast is it traveling right before hitting the ground? 29.7 meters per second. And so would that be positive or negative? Yeah, negative, because it's pointed downwards. So it didn't really ask for the direction, but just you know, check yourself right there and understand that that would be a negative value. So any questions about that one? Yeah, what's up?
So that block would be like any mass, and it would have like the same.
Yeah, essentially. Yeah. Good question. And the reason for that is because we don't take air resistance into account here. And so it doesn't matter what it is, the air is not going to act on it based on its surface area or anything. So any other questions? All right. So moving on to the next one. A car drives off a 90-meter cliff at 30 meters per second. How long does it take to hit the ground, and how far away from the base does it land? So just a quick drawing. You have something right there. Flies off and lands a certain distance away. So that right there is your delta x. This right here is 30 meters per second. This is the velocity it's launched with, right? So it's asking, how long does it take to hit the ground? So it's asking for the time. And how far away from the base does it land? So that's delta t. So right here, I guess we can just write time. Time equals question mark, delta x equals question mark. Those are the 2 values we're looking for. All right, so the thing I like to do is write out every single variable that you're given. So all the x variables, go ahead and write those. So if you guys forgot, you want to make sure you separate those. So our x stuff is going to be initial. We have an initial velocity. So that right there, is there any y component to that velocity? No, so that's just our initial x velocity. Vox equals 30 meters per second. And now what does the final x velocity equal? Right before it hits the ground. This is the math we need to do in our head, right? Because it's not actually any math. If you guys remember, is there any gravity in the x direction? No, there's no gravity in the x direction, right? So the gravity acts in the y direction, and that's why we have initial and final velocities that are different. In the x direction, they're the same, because that's the best way I like to think about it. Just remember, there's no gravity in the x direction. There's no friction in the air. We're not taking in air resistance. So there's no reason for it to slow down or speed up in the x direction. So that makes our acceleration in the x direction what? 0. Once again, like no gravity, no acceleration. All right, so anything else? So That's about all we're given in the x direction, and we're looking for delta x, right? So delta x equals question mark. And so how about the y now? We have initial y equals 0. As you see, there's no y component to that velocity. So you got to break it down step by step, completely horizontal. And that's not just because I drew it. It's just since it's driving on a horizontal road, there's no reason for it to be going in the y direction. Final y velocity, we don't know that, so question mark. Acceleration in the y, we always know that, negative 9.8 meters per second squared. And then delta y, do we know the delta y? Yeah, so it's 90 meters, and so as we said, since it's falling down, is that positive or negative 90? Yeah, negative 90. If you ever forget how to do that, just write out the delta y, final minus initial. Remember that your final position is just 0 because you're on the ground. So negative 90 meters. And so the one variable that acts the same way on y and x, so as you can see, I wrote the time right there. It takes it the same time to go from here, you know, to the bottom of the cliff, which is right here. So it takes it that much time to cover this much y displacement as it takes it to cover this much x displacement. So the t right there, I don't write it in either x or y because it works for both. So in this case, we can just leave t right there. So t equals what? All right, so step one, you're going to see these problems all the time where you're going to have to find t in order to find something in the x direction. Because as you see, in your x direction, you have 30, 30, and 0. So if you try to use kinematics to find more things with that, you're going to end up just getting 0 or something along those lines, and it's not going to help you very much. So you got to use your y values to find the time, and then you can use the time to find something in the x because it works the same way. So first thing you want to do is, I'll write that down, use y stuff to find time. So that's a good, hey Chris. So that's a good general rule of thumb. And so the formula you want to use in this case, you have initial velocity, acceleration, and displacement. So this formula we used earlier, we can't use that because, oh, well, we could use that actually. So that's my bad. You could use that. The thing is, I choose not to because you're not finding time with that. You're just finding your final y velocity. So we have an equation that will let us kind of be more efficient and go straight to finding our time. And so that's the weird looking one. Delta y equals VOYT plus 1/2 AYT squared. So that's just me writing everything in terms of the y direction. So this one right here will let us find time off the bat. And the reason I choose to use it is because we're not going to have to deal with like the quadratic formula or something. Sometimes you might see you have a t and a t squared. In this case, you don't because our initial y velocity is 0, so you can kind of cross that out. So you don't have two t's. And so you have plugging everything in, it's negative 90 equals 1/2 times negative 9.8 times t squared. And once again, writing your 90 as negative is going to let the t be a positive value because you can't really have a negative time. So then all you have to do at that point is solve for time, and you get 4.3 seconds, I believe. And so you found this part. How long does it take to hit the ground? So now what you want to do is find how far away from the base does it land, which is delta x. You got to find delta x. So any questions before we find delta x? Anybody confused about any part of this? All right, cool, cool. So delta x, find delta x using what? How are we going to find that one? We know that velocity equals displacement over time. So that's the one that's going to help you with the delta x, because as you remember, in the x direction, the velocity is the same. So 30 meters per second here, 30 meters per second here. So if it's traveling at a constant velocity, right? So in how much time, or over the span of 4.3 seconds, how far will it have traveled in the x direction? So that's how you can rationalize that. So you know the v equals 30 equals delta x over 4.3 seconds. And then all you have to do is solve for delta x. So a good way to phrase that in your head so it makes sense and you can kind of think your way into this answer is in 4.3 seconds, something going 30 meters per second, how many meters is it going to cover? So in that case, you get 128.6 meters. And it's positive because it's going to the right. So another reason, if you ever get a negative time and you have no idea how you got that and you don't find a mistake in your calculations, you know what, just at that point, if you can't fix that in any way, just make it positive. Just don't write like negative 4.3 because that's what you got. You're never going to have a negative time. So any questions about that? Yeah. Good question, good question. So for this second part, could we use the V final equals V initial squared, right? That one? Let's see. So we know that V final squared equals V initial squared plus 2A delta X. So in this case, we know that they're both going in the same direction. So it would be 30 equals 30 plus 2 times 0 times delta X. So in that case, you kind of cancel out the delta X, so it wouldn't work. So that formula wouldn't work, but if you guys will notice that this formula we just used, this formula you can use for this. It's a little bit like unnecessary because if you guys go ahead and look real quick, delta X equals V O X T plus 1/2 AXT squared. So our initial X is 30, so you're finding delta X, right? So delta X equals 30 times 4.3 plus 1/2 AX, so our acceleration in the X is 0, right? So all that gets canceled out. So plus 0 equals delta X. This right here is the same exact thing as this right here. As you can see, delta X equals velocity times time. Delta X here equals velocity times time. So you end up with the same thing. So you do have options when you're working this kind of problem. So yeah, that's a good question. So don't feel like there's only one way to solve a problem. So any other questions about that one? All right, so let's get to our classic kinematic problem. Football is kicked at a speed of 30 meters per second at an angle of 25 degrees above the horizontal. So go ahead and drawing that, we would get something that looks like this, right? I draw it small just because I never give myself enough space. Let me move that. So it's that right there, 30 meters per second at an angle of 25 degrees. All right, so in that case, if you're given a velocity at an angle, in order to use the kinematics, you have to break it up into its components, right? So go ahead and just do Vx initial equals what? And then Vy, or Vx final, sorry. Oh, no, it is y, sorry. Vy final. All right, so excuse that, just had a little brain fart. So these are both initial, Vy initials equals what? So as you see, this 30 meters per second velocity has an x and a y component, right? And if the ball is kicked at 30 meters per second, that's the initial velocity. So you have an initial x and an initial y. And so we just do the same thing we did when we used the vectors. Our Vy initial is just going to be, so this is the opposite, right? The y is opposite to the angle. And so you get 30 sine of 25. And the x would just be 30 cosine of 25. So always rationalize it to yourself. Don't just assume that x is always cosine, y is always sine, because that's not the case. So just every single time do the little thing in your head. So we found that. And so now what you want to do is write once again your x and your y stuff. So in the x direction, our initial velocity, Vx initial equals 30 cosine 25. So that means that our Vx final equals the exact same thing, and that our acceleration in the x is 0. So At this point, it's kind of just a formality writing these. So it's kind of, once you get that rule, you're not going to have to write it down every single time. It just kind of takes up space. But I just want to make sure we're all clear with that. So the acceleration equals 0, and then delta x equals, we don't know. So it's just a question mark, right? Doesn't necessarily mean we even have to find it. We just don't know it, right? So that was your x stuff, and then your y stuff is going to be Vy initial equals 30 sine of 25, as we can see right here. So that's something I typically, I would recommend you write Vy initial, Vx initial up here, just so that when you're writing these, you can kind of just instantly go back and see what you wrote. And then our Vx, or Vy final, what's our Vy final? What is it? 0. 0. Why? Because it's saying how high will the ball go. So at the highest point of the arc that this makes, the ball is going to have a 0 velocity, right? At the highest point, and then it's going to come back down. So that's how this works. We're doing all our calculations based on that point. So our final point is going to be where the y velocity equals 0, right? So then acceleration in the y, as always, is negative 9.8 meters per second squared. And then our delta y is kind of what we're looking for, right? So we're looking for how high does it go? Well, what's the delta y when the final velocity is 0? So don't think that, so this delta y is just at the highest point right here. All right, any questions before we calculate that? Yeah, good question. So it's 0 because we're taking our y final point to be the highest point. And at the highest point, if you remember, it goes up and then stops and then comes down, right? So it's momentarily 0 meters per second. Any other questions? All right, so then it's really kind of a one-step thing. Number 1, find delta y using y things. So use the y things to find delta y. That one is kind of self-explanatory. And so then you would use your really popular formula, Vf y squared equals V O y squared plus 2ay delta y. Gotta love that one. So then you get final velocity, we said it was 0, equals initial velocity squared, which we said was 30 sine 25. So that's squared, plus 2 times negative 9.8 times delta y. So here, let me move that over a little bit. So yeah, that's just about as zoomed out as this gets, by the way, so it's just kind of close. And so now, solving for that, all you have to do is solve for delta y. So just the one variable, and so delta y equals 8.2 meters. And notice that you get a positive number rather than a negative number. Why is that? Because you went from the ground up to somewhere. It's not like the other problems where we were falling from a cliff and ending up on the ground. We started at the ground and ended up higher, so we have a positive displacement. So any questions about that one? That's like a super typical problem. I see no reason for him to not include like this angled kinematic in 2 dimensions problem. So if you have any questions, feel free to ask.
You square the whole, the initial V?
Yeah, you square this whole thing right there. So 30 sine 25 squared. Cool. So if no questions, we can go ahead and move on to the next question problem. All right, so also FYI, I will be posting these answers, and they'll look a little different because I'm going to be posting ones that I wrote not live, so that it'll be neater and a little bit more explanatory. Because when it gets live, I tend to write really big, and you know how it is. So what is Newton's second law? I just want someone to tell me this one, because you might want to remember Newton's laws. There might be a question on that. You don't want to be caught off guard. What is it? Good. So it's the one that says force equals mass times acceleration, right? So that's where we get that formula. But more specifically, it's the same exact thing, but just do it in terms of A. So A equals F over M, right? because this is the law that lets you know that force and acceleration are directly proportional, and mass and acceleration are inversely proportional, right? So if something is more heavy, so if something has more mass, it will give it a smaller acceleration than something with a smaller mass, and vice versa with the force. So obviously, more force would be more acceleration. All right, any questions about that one? So I just said the second one, so we don't have to write all three. Just remember to take a look at the other ones. Anyone know what that third Newton's law is? Good, thanks Rick. Yeah, exactly. So that's the action-reaction pairs. So that's like when you push a wall, it's kind of pushing you back, right? So number 10. A constant force applied to object A causes it to accelerate at 5 meters per second squared. The same force applied to object B causes it to accelerate at 2 meters per second squared. So which object has the largest mass? So does anyone know? B, good. So B, why? Because it accelerates more slowly. So once again, back to second law, right? So it accelerates more slowly with the same force, so it must be more massive. So what is the ratio of mass A to mass B? So I just do this one because I see he likes the ratio questions. So we might as well get a little comfortable with those. So in this case, what you'd want to do is force. We know it's the same force for both object A and B, right? So it's just force equals mass A times acceleration A, right? So we get that formula. And so just solve for solve for the mass A, because it's asking for the ratios. So mass A equals force over acceleration A. All right, so we solved for the mass of object A, right? Because we don't really have the force number. We do have the acceleration, but we don't have to plug that in right now. So now do the same thing for the other one. And I'm not writing force A and force B because they're the same forces. So that's what makes this whole problem possible. So force equals mass B times acceleration B, right? And so solving for MB, you get F over AB. And so now if it asks for the ratio of A to B, mass A to mass B, you want to do mass A over mass B, right? And so that's going to equal F over AA over F over AB. So this is the part that gets a little confusing. It really kind of applies those, those fraction rules. So in that case, you just want to solve that. You would flip that. So it's essentially F over AA, and then AB times AB over AF. So that's just what happens when you simplify that, so you don't have literally 3 divisions going on. And so what happens there is your forces cancel, and you have values for AB and AA, right? So AB is 2, and acceleration A is 5. And so there's your ratio, 2 over 5. So yeah, try to get comfortable doing ratios, because he's done a few ratios during lecture as well. So just just try to be proficient at those. Any questions about anything that I just did? No questions? Cool. So so now we're moving on to like the section 2, right? So we're done with kinematics. We're kind of going into forces and stuff. So write whether the apparent weight or the actual weight is greater in each of the following scenarios. So before writing this down, we know that apparent weight is what? I think I heard someone say it, I think. What is it? Good, normal force. So that's your apparent weight, right? And so that means that your actual weight is really just what? It's just your mg. Yeah, good. So it's just your mass times gravity. That's your actual weight. It's not going to change ever. No matter what acceleration you're experiencing, your actual weight is not going to change unless you take pieces off you off. So an elevator is moving downwards and is slowing down. So that's our first scenario. So we have an elevator that's moving down and slowing down. So all we want to get from this is what direction is the acceleration pointing in? Up, good. So if the acceleration is up, right, that means that the net force will be in what direction? F net will be up, and so which one's up, normal or weight? Normal. So therefore, in this case, your apparent weight is, yeah, greater. So apparent weight is greater. So we're looking for the greater. So apparent weight is the answer to A. Elevator is moving down and is speeding up. So what is the direction of acceleration? Down, good. So acceleration is down, net force is down. Good. So these are those elevator problems. And so in that case, your actual weight is greater. So same thing, elevator is moving up and slowing down. That means the acceleration would be pointing what? Down, awesome. Down, so F net is down, and therefore your actual weight is greater. And then the very last one, elevator is moving up and speeding up, therefore our acceleration would point up, good, up. So F net is up, and so apparent weight would be greater. Any questions about that? No questions, cool. So that right there shows you that relationship, acceleration and net force will point in the same direction. That's the only way it can happen. So, any questions before moving on to number 12? Bless you. Anybody? All right, so number 12. Consider the following drawing. If the tension label T, so this one right here, equals 125 newtons, then what is the tension in the horizontal string? So right here. So we can call that T2. We're looking for tension in T2. So notice how there's no mass, or really there's no mass or anything given about this ball, right? So you got to use your tension in order to find T2. So in this case, this tension, right, you see how it's at an angle? So that means that you're probably going to have to use your components. So you have your Ty and you have your Tx. So Tx right there just refers to this portion right here. I apologize, I didn't leave much space there. But regardless, in this case, is this ball in movement at all? Can we say it's accelerating? It's staying still, right? So equilibrium. So we know that the net force in the y direction is going to be what? 0, good. And so the net force in the x direction is going to be 0 as well. Awesome. So in this case, in the x direction, we have Tx, right? Tx minus T2, because T2 is in the left, so we say minus. So Tx points to the right, T2 points to the left, and that equals 0, right? So that means that Tx must equal T2. So if we want to find T2, all we have to do is find that x component of the tension. We have an angle. We know what T equals. So all we have to do is find Tx. So then Tx equals, we know it's going to be 125 times, is Tx sine or cosine of this angle? Cosine of 35 degrees. And so therefore Tx equals 102.4, which equals T2. And you find your answer. So about this problem, it can get, the only reason this problem can be tricky is because you might be wanting to see the mass of this ball, you might want the weight of it, right? You might be trying to find that Ty. As you can see, you don't need to do that at all in this case, so always just try to exhaust all your options before you feel like you don't know how to do it. So any questions? Are you guys comfortable with that? You guys cool with tension? Yeah, what's up? Oh, okay, good question. I mean, so in this case, so you see Tx up here, how it's this component? So let me just draw it down here. It's essentially the same thing as doing this, right? So Tx and Ty. So this ball is not moving. So this component of Tx is applying the same amount of force that this component is applying. Or not component, but just this T2. So if they're equal, and this one points to the left, so if I draw the free body diagram, it looks like Tx, T2. So therefore, I would do Tx in the positive, so it's positive Tx minus T2 because it's going to the left. Yeah. Yeah, of course. And so don't even need to look in the y direction for this problem. So any questions? No questions? All right, so moving on to the next question. So here we are at number 13. All right. Box is speeding up horizontally due to being pulled by a tension T. The kinetic friction acting on the box is 25 newtons, while the acceleration of the box is 18 meters per second. We also know that the normal force is equal to 147. All right. So it tells you the normal force for some reason. So normally you're not given a normal force, right? So the only reason it gives you the normal force is because, as you can see, it does not give you the mass of this box at any point. So we might see you needing to use that normal force to find the mass. So let's go ahead and get started with just draw out what is happening. So you have a box, right, that's being pulled by a certain string. We have the weight going down, normal force going up, and we have kinetic friction, right? So notice how I made the kinetic friction vector smaller than the tension. I did that on purpose because it says it's accelerating, right? And it tells you the acceleration is 18 meters per second to the right. Because it's not only is it positive, but it can only be pulled by the tension. So we know that it's moving, it's accelerating to the right. And so in this case, let's just go ahead and write out what we know. So we know that acceleration equals 18 meters per second squared. Kinetic friction equals 25 newtons. The normal force equals 147 newtons. And then the tension equals question mark. We don't know it. So just don't make the mistake on your test of tension and period. Don't get those mixed up. I have a question later on that has both tension and period in the same question. So hopefully just what I like to do is I like to draw a vector over the t's for the tension. So that kind of reminds me it's not period. All right. So once again, let's just draw that free body. But let's draw it like actually correct. So we know that up is normal force, down is mg, and they're equal, right? Because the box is not accelerating up or down, right? It's moving only in the horizontal direction. Kinetic friction to the left. To the right, we have tension. All right, so in this case, first thing you want to do, because if you're looking for the tension in the rope, you need to find the mass of this first. Because why? Because if you were to write this out, it's tension minus kinetic friction equals MA, right? So we'll get to that in a minute anyway, but MA requires the mass. So just know if you don't have the mass, just try to find it. So you know that your net force in the y direction, is it accelerating in the y direction? So what is that? 0, good. So equals 0. So that means that normal minus mg equals 0. Therefore, normal force equals mg. So, and that makes sense. It's not accelerating up or down, so n must equal mg, right? So you don't even have to write all that stuff once you get more comfortable with that. So we know that 147 equals mass times 9.8. And therefore, your mass will be equal to 15 kilograms once you work that out. Remember, don't write g as negative 9.8. If you do that often, make a note not to do that, because that will change your answer. All right, part 2, now we're actually going to find the tension. So to find the tension, just use your same free body diagram, because you know that the net force in the x direction, is that 0? No, because we have an acceleration. Good. So we know it's mass times acceleration. That's why we had to find the mass, because we need that. So the forces in the x are T. As you can see right there, it's T. That's in the positive direction. And F is in the negative direction, so it's T minus F equals MA. And so we have T minus 25 equals 15 times 18. And you're just left with T equals 295. So in my opinion, there's like a pretty decent correlation based on how neat or organized you write your steps out with how often you get the answer right. So this is not one of those, this is not the subject where you want to write all over the page, right? Because things tend to follow specific procedures or steps. So in case you are one of those people, try to make it neater and see if that improves your accuracy a little more. And it also helps you rationalize through problems a little better. So any questions about that one? All right, so moving on to number 14. So Jack has a mass of 58 kilograms. He's standing on a scale in an elevator that's accelerating downward at 1.7 meters per second. What is the reading on the scale? So the reading on the scale in this case, what's another word we can call that? Is it going to be the same as his normal weight? No, we call the weight on the scale what? Yeah, apparent weight. So we're looking for apparent weight, which in this case is, as not just in this case, but we said apparent weight equals what? Normal force. Good. So apparent weight equals normal force. So I'm just going to write that better just because we have W's now, omega, so I'll just write apparent weight equals normal force. All right, so if we're looking for, essentially we're looking for the normal force. So that's really the main thing it was testing you. That's what that problem will be testing you on. Do you know what apparent weight means, right? Because now finding the normal force is not super involved. So let's go ahead and do it. We draw a diagram, free body diagram. He's standing in an elevator, so there's only stuff in the y direction. So it's accelerating down, right? So that means that your weight, your mg, should be greater than your normal force since you're accelerating down. That means the net force also needs to be pointing in the down direction. All right, so then we know that net force in that direction is going to be equal to mass times acceleration. It's not equal to 0 because it is accelerating. And so we know that normal force minus mg equals ma. Therefore, normal force equals ma plus mg. Right? So in that case, your mass is 58 times your acceleration, which is negative 1.7, and plus 58 times 9.8. So right there, another little part that might have gotten you is that you have to, if the acceleration is pointed downwards, you want to show that when you plug it in, negative 1.7. So now in that case, we get 469.8. The gravity? That's a great question. So why did we not input negative 9.8, right? So the reason for that is because we already did n minus mg. So when we did n minus mg, we showed that the gravity goes in the down direction. And then in that case, if you don't like plugging in the negatives, like that, you can always do n minus mg equals negative ma to show that the acceleration is downwards, and then you can just plug in 1.7, but it works either way. So just whatever you're comfortable with. 469.8 newtons. So in that case, we're just saying that the weight is going to be in newtons, or the apparent weight. Any questions about the apparent weight problem? All right. So when dealing with forces, acceleration and net force will always point in what? Which one is it? Same direction. Awesome. That's just super important. So make sure you understand that. It's going to help you through a lot of these chapters. So moving on to 16. Any questions before starting on number 16? All right, so use the picture below for the following question. It makes sense. Ramp below is frictionless, so no friction. That's good. Block M has a mass of 10 kilograms, and block also M, but lowercase, has a mass of 5 kilograms. So just go ahead and write that. 5 kilograms, mass equals 10 kilograms for the uppercase one. All right. And the angle theta is 40 degrees. So theta equals 40 degrees. So I wrote 40 degrees right there. If the two blocks are released from rest, what direction will the 10 kilogram block travel? So if they're released from rest, what direction is this bigger block going to travel? Is it going to go up the ramp or down the ramp? You have to calculate it. You might think it's intuitive, but sometimes it is, sometimes it's not. So it's complete guesswork if you don't calculate it. What will be the magnitude of its acceleration? So first thing we have to do is find whether it's going to be moving left or right. So what I like to do is just think of it as simple as you can. Which one is pulling harder? Okay? So we know that this one is pulling downwards with lowercase mg, right? That's the weight. That's all that it's pulling with. Okay? This one right here is pulling with something in this direction. So what's the only thing that kind of points in that direction? Does this have friction? So no friction. So in this case, it's the weight. Okay, so which one is it? Mg what? So I'm just going to make it a little smaller to have space. Here's a little mnemonic device. Mg sine down the incline. So down the incline is mg sine. Because why? Because you know our weight goes straight down, right? So that means that there is a component that goes down the ramp and a component that goes this way. So we just really care about this one, mg sine of 45. Or not 45, my bad, it's 40. Mg sine 40 degrees. Yeah. Mg sine down the incline. So, everyone got that? So don't use the entire weight of the 10 kilogram block as the force that it's pulling with, because it's not. It's only pulling with that component of weight, right? And so now all you have to do is calculate which one of these is greater, which one's going to pull harder. So we know that mg sine of 40 is going to be equal to, oh, that's here, real quick. Fix this in case you wrote it. I hate these types of problems. The m, it's uppercase M, just so that you can tell the difference. So it's mg, not mg. It's mg. So uppercase M. Mg sine 40, right? So we get 10 times 9.8 times sine of 40, and that is 63 newtons. All right, so we got the first one. And now let's see what little mg is. Mg is 5 times 9.8, which is just 49 newtons. So which direction is this block going to travel? Up the incline or down the incline? Down the incline. Awesome. So just block M, capital M, will travel down the incline. Cool. Now, what does that mean? So what is the magnitude of its acceleration? So we're just looking for the magnitude, not specifically a direction, but just why not? What is the direction of the acceleration for this block? Left or right? It's left, right? That means that if it's going to be moving down the ramp, it's because it's going to need an acceleration that way. So the acceleration moves down the ramp. And then for this one, is it moving up or down? So the acceleration for this one points in what direction? Up, yeah. So acceleration and the direction it's moving in don't always correlate necessarily. But in this case, you know that it went from rest to moving this way. So it has to accelerate in order to move if it's going from rest. But now what we have to do is do our typical finding the acceleration or tension from two blocks in a ramp or whatever. So just draw the free bodies for both. So free body for M right here, we know that, here we go. So we know that And just don't write it at an angle. Just write it as if this is the incline and it's straight, just for convenience sake. We know that there's tension, and we know that a greater force, mg sine 40, goes to the left. So let me write that a little smaller just to make it more obvious. That right there, right? And in this case, we're not worried about the things in the y direction just because we're only dealing with tension and acceleration. So all that's happening in the horizontal direction. And then for this block, we have, let's do it over here to be greater. Upwards, we have tension. And down, we have mg, but smaller, right? And here we go, I did it again. So that's capital M for this one. I recommend if you get this problem on a test, just write M1, M2. That's what I feel like I should have done. Because capital M, lowercase m, it's kind of hard to remember. So here we have this, and now we just want to come up with the formula for each one of those. So for this one, we know that T minus M, capital M, mg sine 40 equals ma. So positive force to the right, and then plus the negative force, which is minus negative mg sine 40, equals ma. And one more thing right there that you don't want to miss. It's like, this is how easy it is to miss that I just did. First of all, what direction is it accelerating in? Did we say right or left? So it's equals negative ma. So that right there is another thing that will trip you up. Once you do these enough, you're going to start, now, these signs start kind of looking like the same thing. So think about every step of the way. So then now for this one, we want to write an equation as well. We know that T minus mg equals ma. And in this case, the acceleration for this block goes upwards, right? So the acceleration is not negative because up is our positive direction. So any questions about that? Cool. All right, cool. So T minus mg. So in this case, if we're looking for acceleration, then you'll see that we don't know tension and we don't know acceleration in both formulas. So you want to solve for tension in one of them so that you can get the acceleration in the other. So here we know tension is going to be equal to ma plus mg. And so you can plug in that T into this T right there because they're the same tension. And so you get ma plus mg minus uppercase mg sine 40 equals negative ma. All right, so it gets a little long. And so now all you have to do is plug everything in and solve for your acceleration. And so that would leave you with, so 5a plus 49 minus 98 sine 40 equals negative 10a. So now at that point, all you have to do is solve for the a. I just kind of multiplied the things out, and so you get a equals 0.93 meters per second squared. Yeah. Is it what? Yeah, so that exactly. So in this case, like you could just take this to this side and make it like negative 15a equals all this stuff, or you can bring it this way. Yeah. Yeah, that's what makes it weird, exactly. There's two T's, two A's in both equations. You just got to plug one equation into the other, essentially. So that's your most typical tension problem that you'll see. I mean, it's really in almost every test that involves tension or forces. So it's really good to understand this. Any questions about it? Everyone clear on why that's negative ma right there? Yeah? All right, cool. Just make sure you do that. It'll change your answer if you don't. So moving on to the next question. All right. So also a tension problem. Two blocks are connected by a string using a frictionless pulley as shown below. So it's a frictionless pulley. What is the acceleration of the upper block if the coefficient of kinetic friction between it and the ground is equal to 0.2? So the pulley is frictionless, the ground is not frictionless. So a common problem with this one, and it's really probably just due to the wording, I drew this one, so there's only friction between this and this box. There's no friction between this box and the wall at all. So don't try to incorporate that. So now to get started, my bad. All right, you want to go ahead and draw your free body diagram. Cool. So we're looking for an acceleration in the end. So our end procedure is going to be essentially the same as the other one, where we're going to do two equations, plug one into the other. But this one is about kind of just starting it. So we have normal force up, mg down, or m1g down. So this one, we're doing this box, m1g. And then to the right, we have tension. And to the left, slightly smaller, we have kinetic friction. So we know that the box is falling to the right, so it's essentially the acceleration is going to be pointing to the right. So now, what is this kinetic friction? Because you want to be able to use that when you're trying to find the acceleration, because you can't have tension, kinetic friction, and acceleration all missing, because then your equation won't work. So Fk, so first of all, the formula for that is coefficient of kinetic friction times normal force. It's the same for static friction, so that would just be Fs equals mu s times normal force. So, but in this case, we're dealing with kinetic friction. And so that means that Fk equals 0.2 times normal force, which in this case, as you guys can see, your normal force is equal to mg, right? So it's just 0.2 times m1g. So you can replace normal force with mg if it's not moving either up or down, which is not. And so you get kinetic friction equals 3.92 newtons. Excuse me. So any questions about how we did that? Anybody? All right. So at this point, it's just back to the basics. You want to write your two formulas, one for each one. So this was M1, this one will be M2, right? And so for M1 we have, as we said, T minus Fk equals M1A. So M1A, and it's not negative because the acceleration is pointed to the right. And then we have, for the other one, we have T minus M2G equals negative M2A, because the acceleration is in fact pointing downwards in this case. So any questions about that? Because this block is accelerating downwards, therefore you show that by doing negative M2A. All right, so now same exact procedure. We can go ahead and just solve for T in any one of them. I'll just choose this one because it looks a little smaller. T equals M1A plus force of kinetic friction. Therefore, we can even simplify that a little more. T equals M1, which is 2. So 2A plus 3.92. So then we can go ahead and plug that T in to that T. So I'll just do that. So we get 2A plus 3.92 minus M2G equals negative M2A. And so we get 2A plus 3.92 minus 9.8, because our mass 2 is just 1, equals negative A. And so once again, this just leads you to your typical solving for A, and you get acceleration equals 1.96 meters per second squared. So that just tells you the magnitude of the acceleration. And then if it asks you the direction of the acceleration for a specific block, you would say, for this one, it's negative 1.96. For block 1, it's just 1.96 because it's to the right. So any questions about any of that? So yeah, it's just about the same as the last one. So I'll give you guys a minute to write that down. So next question, I want one of you guys to tell me this one. Formula for force due to gravity. Does anyone remember that formula? Yeah, that's the one with the big G in it. Maybe that'll... I'll start us off. F, because it's a force, right, equals what? So G good. MM, or just write M1, M2, so you know there's two different masses, over what? R squared. Awesome. So that good old formula right there. If I remember correctly, during his, what is that, his top 10 list before the final, he said you're not going to get any of those crazy problems that involve this equation with the two planets and the satellite orbiting, whatever. So ideally, that's the case. But either way, we still want to cover the basics of it, right? So we'll get to that in a minute. Just make sure you keep that formula in mind. And then before that, a couple conceptual questions. A car is moving at a constant speed down the road. When it reaches a semicircular dip in the road, at the very bottom of the dip, which of the following must be true? So car reaches a dip, and it's right here. So which one is true? Go ahead and read through those and tell me. So I got A. All right, that was pretty quick. Awesome. The normal force is greater than the weight, and why is that? Anyone know? Good. Awesome, good. So in this case, the acceleration is the centripetal acceleration, right? And we know that points towards the center of a circle, correct? So if the acceleration is pointing up, the net force must also be pointing up. Therefore, the normal force must be greater than the weight. All right, cool. So any questions about that one? All right, the next one, because it's the same exact thing. A car is moving at a same thing, right? When the car reaches the peak of the hill, which of the following is true? So now we have the car right there. So what do you got? B. All right, good. So it's just the opposite. So the rationalization for that, centripetal force points towards the center. The center is downwards. Downwards is negative. The acceleration is negative. The net force must be negative, pointing downwards. Therefore, the weight points downwards and must be greater than the normal force. So any questions about that one? Just like the other problem. Cool. So as you can see, we kind of moved into that circular motion chapter. So a man attaches a 5-meter rope to a shopping cart with a mass of 20. So he grabs the free end of the rope. So essentially, it's just the man, in case the problem's kind of confusing, he has a rope. He has a shopping cart at the other end, and he's spinning around in a circle, spinning the shopping cart around him. And then it just gives us some facts about it, right? So what we could do is draw the circle, right, from the top view so we can see the whole circle. And say we're taking the shopping cart at this point. Why not? You can pick any point to do this, but why not pick a reasonable one? So then we have mass equals 20 kilograms. Tension equals 110 newtons, as it says in the problem. And the radius of the circle is 5 meters. So all good stuff. They're giving you radius now, right? So this is probably going to involve some centripetal equations. We'll see. So at this point, we know that the tension points inwards because that's where the rope is. The guy's in the center, so the tension is in the rope, right? And that's just about the only force you can draw. We have weight and normal force, but as you can see, this is a top view, right? So we can't really draw those. They cancel each other out anyway, so it's fine. So we just have the tension. So now what you want to do is write your sum of forces equation. So sum of forces, in this case, are they equal to 0? So ask yourself, is there an acceleration happening here? Yeah, there is, right? And what do we call that acceleration? Centripetal acceleration. Good. So we know force equals mass times centripetal acceleration. So sum of forces, what's my only force there? Tension, right? And what direction is it pointing in? To the left, right? So negative t equals, and in this case, what direction is the acceleration pointing in? Towards the center. The center is to the right or left? Left. So then you can do negative m AC. So I just do that to illustrate a point that the net force and the acceleration are always going to go in the same direction. So this is a problem where even though it's going left, you really don't even have to show that just because it'll work out anyway. I just do it so that you guys can see how it works. So I like doing it, but you don't really have to. So a technique is that even if you're using this point right here and everything's to the left, you can just leave it positive because it's the same thing. So this is one of those instances where that's the case. So we'll just leave it positive because it's just easier, right? No negatives. So in this case, acceleration, centripetal acceleration, what's the formula for that? Just the centripetal acceleration, what is the formula? Close. V squared over r, yeah, but yeah, that was close. So in this case, you can write mv squared over r. We just replaced the a with v squared over r. And now we plug everything in. We have 110 for the tension equals a mass of 20 times a certain velocity squared over 5 meters, because we don't know the velocity, right? And so solving for that velocity, we get, go ahead and try that for a second. Someone just tell me what that equals. 5.24, thanks Rick. So 5.24 meters per second. Cool. And so did we find the period that it's looking for? How much time does it take the cart to make one whole rotation? No, that's the velocity. So I guess here I didn't highlight that. How much time does it take for the cart to make one whole rotation? So we call that what? Yeah, period, right? So we call this, so this one right here has a tension. Good thing I've been writing my vector symbol over the t. So, because now we're looking for t, period. Period. We're looking for that, right? And so what formula do we have that has velocity and period in the same equation? Yeah, like honestly, you guys got the formula sheet, right? We know velocity equals 2 pi r over t, right? Do you guys remember from like your newest stuff how omega equals 2 pi? Omega equals 2 pi over t, over t. So this one has the r because it's not omega, it's velocity, so it actually adds the meter component to it. But anyway, so that means that t must equal 2 pi r over v, right? Just because you multiply the t over here, divide the v over here, and that just makes the problem a little nicer to solve. So you get 2 pi times 5 over a velocity which is 5.2. And all that equals 6 seconds. All right. So any questions about that one? It's a formula that needs to go on your formula sheet in case it isn't already. All right, so any questions so far? All right. So number 22. A ball is attached to a string and it's being spun around in a vertical circle at a constant speed. Which of the following is true? So go ahead and take some time to answer that one, and someone just tell me what they think the answer is. C, thank you. So why is that? Is because as you're spinning around in a circle, it says you have a constant speed, right? But speed is not the same as velocity because velocity takes the direction component into it. So the velocity here points that way, velocity here points that way, et cetera, right? So the non-constant velocity, because it's changing directions, as vectors do. And why does it have a non-zero acceleration? For the same thing. So acceleration here is centripetal acceleration. It points towards the center, center, center. Those all point in different directions as well. So answer choice A kind of sounds right, but it's still not correct. So remember, acceleration is not speed over time, it's velocity over time. So any questions about that one? Anybody? Cool, cool, cool. Just a little concept. All right, so number 23. Planet 1 has a free fall acceleration of 5 meters per second squared at the surface. Planet 2 has 2 times the mass and 1/4 the radius of Planet 1. What is the acceleration due to gravity on Planet 2? I remember him stressing this one during lecture as he was covering it. There was a problem like that on the test, so we want to make sure we're good with solving that just in case he throws that at you. So we know this formula, G, and in this case we have two. We have G, free fall acceleration of planet 1 and 2, so you just want to signify that you're doing number 1. G1 equals G m over r squared. So that's just the formula right there. Free fall acceleration equals G, mass of planet over radius of planet squared. So why did I not write m1 r1? Because it tells you that planet 2, it tells you its mass and radius in comparison to this one. So as you can see, when we go to write that down, we get G2. We know the G stays the same. Your gravitational constant, it just remains the same since it is a constant. But it tells you that planet 2 has 2 times the mass, so that's G2m. So 2 times the same mass, so that's why you don't do mass 1 and mass 2, over 1/4 the radius. So 1/4 r squared. So don't make the mistake of putting the 1/4 outside of the squared, because it still gets squared because it's part of the radius. And this is what leads you to that relationship that you get between mass and radius with these equations. So just to simplify it out, you get G, or even better, you get 2gm over, so 1/4 squared, you get 1/8. 1/8, yeah, exactly. So then you get 1/8 r squared. So 2 over 1/8, it's really the same as doing 2 times 8. So you get 16 gm over r squared. So what does that mean? The G2, yeah, what's up?
Isn't that 1/16?
What is it?
You square 4.
Oh, 1/16. Oh, yeah, thank you. Sorry about that. I appreciate that. So 1/16, and then, so it's the same thing as doing 2 times 16, and so you get 32. And so in that case, your G2, so your free fall acceleration of planet 2 is 32 times greater than that of G1. So therefore, you know that your G2 is just going to be 32 times G1, bless you, which is just 32 times 5 meters per second, so squared. And so you get, what do you get with that? What is that? 160. And the units for that would be what? Meters per second squared, thank you. So that's how you would get an actual value when they don't actually give you any masses or gravities or radius, I mean. Any questions about that one? Yeah, what's up? What happened? Where? Right here? Or here? Here? The r, that's the r squared. What do you mean? So this whole gm over r squared is still there, but you just know that 32 means that G2 is 32 times greater than G1. Exactly, yeah, okay, yeah, great, okay, yeah, good point. Yeah. Okay, so you make a good point. I didn't mention that at all. Another way to think about it is instead of just saying it's 32 times greater, you can see this exactly as G1, since G1 equals Gm over r squared. So yeah, you make a great point. Thank you. So that's another thing you can do. So any other questions about that one? All right, so moving on. All right, section 3, why not, real quick. A work problem. A woman in a strongman competition exerts a force of 8,500 newtons. So we have the force at an angle of 25 degrees above the horizontal on a car and manages to push it for 500 meters. So we have a distance. So after she wins the strongman competition, she dies. How much work did she do? So work equals FD cosine theta, right? And so this problem is super simple when you just use the formula. You have 8,500 times 500 times cosine of 25 degrees. And that's just a quick work reminder. And you get, it's a huge number. You get 3851808 joules. So work formula right there, just applying it. All these work problems are just variations of the same thing. You can either have them with an angle or without an angle, but just remember a quick note. The reason that it says cosine theta is because only the force in the same plane as motion can do work. So that's just a quick point. So only because she made a force 25 degrees above the horizontal on the car, which is kind of a waste of force because whatever force was directed downwards did no work. Only the force directed horizontally did work. So that's why, for example, as you're walking, you're doing work, but your normal force does no work, nor does your weight, because they're pointed perpendicular to the direction that you're walking in. So, any questions? Is ready to move on? All right, so here we have an energy problem. So energy problems can be pretty simple, so don't not practice them. Make sure you're good with those so that you can get them on the test. So you have a polar bear slides towards a 5-meter tall slide. So that's 5 meters. Excuse me. All right, so 5 meters, and it slides. It slips onto the slide and falls down here, and then it asks what velocity will he be going at the bottom of the slide, right? So we have an initial. So the polar bear starts off right here, and then we have a final. At the end of the slide, how fast is he going? So initially, right here, he's moving 18 meters per second. So does he have a kinetic energy? Yes or no? So there's KE. And does he have potential energy? Yeah, so there's KE and potential energy. Now down here, does he have any kinetic energy? Kinetic energy, yes. He's still moving, right? We're trying to find that velocity. Does he have potential energy down here? No, yeah, like relatively to being up here, he does not. So then only, initially there's both kinetic and potential, and then finally there's only kinetic energy. So now you just use your normal formula, delta E plus delta E thermal equals work. So just your typical thermal energy and work are in there. So is there any thermal energy here? No, why? Yeah, there's no friction, good. So close that. Work, is there any work being done here? Are there any external forces acting on him? No, so work equals 0, therefore delta E equals 0. So you know that delta E equals 0, and so now delta E, what are all the energies present? You have delta KE plus delta potential energy. By the way, I'm writing PE for potential energy instead of UG, but it's the same thing. So KE plus delta PE equals 0. And so to expand that even further, you get KE final minus KE initial plus PE final minus PE initial equals 0. So the reason I don't write formulas yet is just because we're going to cancel some of these things out, so I don't want to write formulas for things that we're going to cancel out anyway. So we said that initial, we have potential and kinetic, so both the initials stay, but final, we just have kinetic energy, right? So our potential energy final is going to be 0, so you can cross that out. And so now you can write in your equation 1/2 mv final squared minus 1/2 mv initial squared minus mgh initial equals 0, right? And so you have everything to plug in to find your final velocity. So in that case, all you have to do is 1/2 mv final squared is equal to, since these are both negative, I'll just take them both to the other side, and we just get 1/2 mv initial squared plus mgho, and then essentially you just solve for your final velocity, which I'll just go ahead and do. So once you have it like this, you guys can see how everything has a mass that's the same. So your mass can cancel out, so you don't have to worry about that. And so you're left with 1/2 vf squared equals 1/2 times initial velocity 18 squared plus g 9.8 times 5, which is the height, like that. And then now that's just getting more clear that at that point we can just solve for final velocity doing some algebra, and we get 20.5 meters per second. Any questions about that? Is everyone clear on why there's no thermal energy and why their work equals 0? Anyone have any questions about that? Yeah. If there was thermal energy, they would say that the slide is not frictionless. And so as he's sliding, he's losing some speed due to thermal energy. Yeah. Cool. So everybody ready for the next question? All right. So this one right here, it was on one of your previous tests, on the energy test. So I figured we might as well cover it. Since he made it a free response question, he could potentially ask a similar question. So a sledder starting from rest slides down a 10-meter high hill. So same thing, right? So we have a sledder right here. So initial, once again, and final, or not even actually, because as it says, slides a 10-meter high hill, and at the bottom there's a long horizontal patch of rough snow. So that's the patch. The hill is frictionless, but the coefficient of friction of the rough snow at the bottom is 0.3. How far will the sled slide along the rough patch? So we're looking for delta x, essentially. How long does he slide before he comes to a stop? So that right there is our final scenario, where he comes to a stop after sliding some distance, right? So initially, he's at rest, so is there kinetic energy? Is there potential energy? Yeah, so initially we just have the potential energy, and then final, he's come to a rest, so is there kinetic energy? No. Is there potential energy? No, so there's none of that really. So all that there is really is the initial potential energy. So now we want to say delta E plus thermal energy equals work, just to write our formula down. All right, so we have that. Now, is there work being done here? I heard what? No. Okay, cool. So can anyone tell me why? Good, no external forces. It's just this friction right here is on the earth. Therefore, there's no external forces. Now, is there thermal energy here? Yeah, why? Because we have the friction, right? So thermal energy, we said, equals, does anyone know what the equation is? I gotta start F, kinetic friction times what? Yeah, X, delta X, good. So as you can see, that's kind of like the work formula, right? Force times the distance. It's just a specific work of thermal energy. But there's no actual work. It's just showing that it is kind of like the work formula. But regardless, we need to find Fk. So Fk equals, we know that's mu k times normal force, right? So we know that's mu k times normal force. So the mu k, or the coefficient of kinetic friction, is 0.3. And our normal force in this case is the same as mg, as it is in a lot of cases, right? Because he's not moving up or down, at least not he's not flying or sinking into the earth is what I mean. So mg, and so we get thermal energy equals 0.3 mg delta x. So that's kind of what we have up to this point. You can multiply the 0.3 with the g if you want, but as you'll see in a little bit, that's really not necessary. All right, so moving on back to this equation. So we said all that equals 0, so the delta E. So there's no kinetic energy at all, right? So it's really just delta PE plus delta ETH equals 0. So potential energy final minus potential energy initial plus, we might as well plug that in now, 0.3 mg delta x equals 0. So initially we have potential energy. Do we have any potential energy finally? No, so you cancel that out. And so you get, if I just go ahead and see how that's negative potential energy initial, I'm just going to move that to this side. And so you get 0.3 mg delta x equals mgho. I just replaced the PE with mgh, right? And so at this point, we can start canceling more things. So the masses on both sides, right? The g is on both sides, so you can cancel that out too. And it just leaves you with 0.3 delta x equals h initial. And so we know that the h initial is what? 10, right? Equals 10. And so we get delta x equals 33.3 meters. So it's not, this problem's a lot easier than it seems. There's several ways to solve it. This is by far the quickest way to solve it. The second way to solve it is, and I'm not going to do it, I'm just going to explain it a little bit. You can find initial and final. So you can do initial and final right at the bottom of the hill before it hits the rough patch, right? So there is kinetic energy here. And once you find those values, you can do initial here and final here to find how far it goes. But it's really unnecessary, but it does work out, as that's how I used to do it. So it does work, but once again, it's really long and unnecessary. So any questions about this problem? All right, everyone clear on the work and thermal energy? Because that's kind of crucial to these problems. So if you have any doubts, make sure you raise your hand. All right, so here we are, number 27. Okay, so these are cool. This is your classic ice skater problem. Two ice skaters, Jacob and Mark, standing facing each other on frictionless ice. Jacob has a mass of 60 kilograms. David has a mass of 75. They push off from each other. And after the push, it tells you that Jacob moves at a certain speed. So what's Mark's speed, right? So in this case, what you want to do is, this is a problem that relates to the conservation of momentum, right? So it's frictionless ice. They're not losing any velocity. So we know that conservation of momentum means change in momentum equals 0, right? Delta P equals 0 because your momentum is not changing. Initial to final, it's the same, right? And so what do we know though? We know that the initial momentum equals 0 because they're standing still, right? So initial momentum equals 0 because they're not moving. So that's going to help because we know that delta P is just P final minus P initial equals 0. So if P initial equals 0, cancel that out, and you're left with P final equals 0. So what is P final though? Your P final is M1 V1 plus M2 V2. Why? Because this is the momentum of, Jacob, and this is the momentum of Mark. Both of them make up the final momentum after they're moving. So another thing actually you could write is just so you don't have to worry about the signs later, just write minus M2 V2. Because why? One of them is going to move in a positive direction. The other one's going to be moving the opposite direction, right? So they don't tell you which one's moving in the positive one. I guess it tells you the Jacob's moving at a speed of 2.5, which can be positive. So this is Jacob positive, Mark is negative. So this just turns essentially into m1 v1 equals m2 v2. So, I mean, it turns into, you can go, once you see this problem on a test, you can go straight to this formula now, as long as you understand where it comes from, right? And then you can go straight to that one, making the problem a lot faster. So mass 1, so 60 times 2.5 equals 75 times V2. And then you can solve for V2 and get it that it's going to be equal to 2 meters per second. What's that? All right. Any questions about this? Mm-hmm.
So David is supposed to be Mark?
Did I say, is David up there?
Yeah, the question.
Yeah, David's supposed to be Mark. Yeah, sorry about that.
Okay, so
I'll make, yeah. Mark. So that's Mark right there. That's my fault. Yeah. What's that? Negative. Oh, yeah, great. So in this case, we found the magnitude of his velocity. But if they ask you what direction it's going in, he's just going in the negative direction, or you could say it's -2. So, yeah, thank you. That's a great point. All right. Oh, hey, so real quick, before we continue, I just want to pass this out for you guys to fill out as you go along. Can you start passing these down? They're just surveys that are meant to be passed out just so that you guys can help improve the program with your criticisms and that kind of thing. So just feel free to fill those out as you keep listening. And then just at the very end, try to leave them on your desk so that I can pick it up or hand it to me or whatever. Just try not to take it with you. And make sure everyone gets one. They're going around right now. But yeah, so other than that, let's go ahead and keep going. So number 28. So this right here is a 0.4 kilogram particle is moving towards the right at 2.5 meters per second, is going to collide with a 0.8 kilogram particle that's moving to the left at 1.5 meters per second. The collision will be perfectly inelastic. In which direction will the particles move after impact? So this right here is a conservation of momentum problem. And we are told that it's perfectly inelastic, so that's good. So right here we have a particle moving to the right, particle moving to the left, and afterwards they're going to collide and stick together, right? Because it says it's perfectly inelastic. So inelastic means that they stick together. So it's asking in which direction will the particles move after impact. So that's what we're trying to find here. So velocity of the first one is 2.5 meters per second. The velocity of the second one is 1.5 or negative 1.5 meters per second. So that right there just says negative 1.5. I'll just point at it because I wrote that pretty bad. All right, and so we're trying to find the final velocity here. So how many masses are there before the impact? 2, right? So all you want to do is show that in your formula. M1 V1 initial plus M2 V2 initial equals how many masses after the impact? 1. So we can call that capital M is just the sum of both masses, and then whatever final velocity that's going in. No, thank you very much. All right, so we have M1 is 0.4 kilograms times V1, which is 2.5, plus 0.8 kilograms times negative 1.5. So don't forget to include your sign there because that's going to change the whole outcome of your problem. So negative 1.5 equals 1.2, because that's just both masses added up, 0.4 plus 0.8, times VF. So you're finding the final velocity. And then you get VF equals, just go ahead and solve that and somebody tell me. What was that? Negative 0.03? Okay. So I got negative 0.83. Did anyone else get that? So I'll just assume that that's the answer. So, I mean, the math is right. So if this, just do it on your own whenever you have a calculator. If you don't have one, make sure you get the same thing. But moving on. So this next problem is also the same type of problem, momentum problem. Would you guys like to skip it to move on to the next stuff? Yeah, cool. So what do you guys say? Do you guys want to skip towards like the last things? Like, since we don't have a lot of time, maybe like chapter 14 stuff, right? So why don't we go ahead and get a little bit of that. On my WordPress site, which I'll just write up here real quick, not the study union one, but mine, ucfsi.wordpress.com. I have like a little, my own kind of make formula sheet for chapter 14. If you guys want to look at that, if you haven't seen it, I tried to include all the formulas that I thought were most useful and an explanation of when you would use them. So that's why I kind of kept this brief. It's only one page of chapter 14, since it's not like the test is going to be focused on 14. It's going to be proportional for every chapter. So try not to spend a crazy amount on chapter 14. Do everything equally. But I did upload a formula sheet for you guys. And do you have a question? 0 for the momentum problem? To the momentum problem. So real quick, let's just check that. Where were we? Here we are. So can we get someone else to just double check that problem real quick? Negative 0.16? 1.16. 0.16? Negative 0.16? All right, I got like 2 people with that, so we'll stick with that. I mean, so it seems like, I'm not sure why the 0. Are you putting this is negative right here? Okay, good. So it seems like negative 0.16 is the answer we're agreeing on. So thank you guys. All right, so moving on to the last page. All right, so here we go, section 4. All right. So a pendulum has a period of 2 seconds. What is the length of it in centimeters? So period formula for a pendulum. Anyone know that off the top of their heads? No? 2 pi square root of L over G. Awesome. So as you can see, there's no mass anywhere here. So the mass of whatever's attached to the end of the pendulum does not affect the actual period or frequency. So that's kind of a concept that you might be asked about. So just see, there's no mass here. So mass does not affect that. So then you get 2 pi. Essentially, it tells you the period of 2. So what is the length? So 2 equals 2 pi square root of L over 9.8. And so at that point, all you have to do is solve for L. So you'll find the period in meters. And I'll just do that since we're kind of running out of time. As I said, I'll post the answer key. So it'll get in meters, so don't forget to turn it to centimeters. Yeah. The answer sheet should be, I mean, I'll upload it by tonight. So if you're going to be looking for that, it'll be by tonight. Don't forget that on my WordPress site, there's also more extensive reviews that I did for tests 1, 2, and 3. So if you feel like you want to go more in depth, go look at those. I just didn't want to make this review. As you can see, like we're already running out of time. So they go more in depth, and I have the answers put up for every single problem that I've done. So you go ahead and do that for more extra practice. So what is the period of a 2-meter long leg of a person walking? So this right here is called, does anyone know what this type of pendulum is called? Physical pendulum. Cool. So it's asking for the period, right? So t equals 2 pi, but now what's in here changes. So can anyone tell me what that is? Formula for a physical pendulum? What's that?
Oh, something over the inertia.
Yeah. Something over inertia, right? Is that ringing any bells with anyone?
There's mass on it,
Good.
but it cancels off each other.
Yeah, but we get mass. We know we have D and L, good. So MDL. So the D stands for center of gravity. Or yeah, it's just the D is for like distance, I'm imagining, but that's like the center of gravity. So in this case, you have a leg. So think of it this way: a leg around a hip joint. All right, so that just means we have about 10 minutes left. So that's a leg around the hip joint. So you want to find the I for a thin rod that rotates about one end. Does anyone know what that is? It's the center of mass. So, I mean, granted, I don't actually know that one off the top of my head just because they're in the book.
I is mr squared, right?
It's like yeah, it's something M L 1/3. Okay, thank you guys. So it's 1/3 M what? MR? L, yeah. Yeah, it's the same as L, but so L squared, good. And then in this case, the D, center of this right here, is where is that on this rod if the mass is spread evenly throughout? It should just be right in the middle. So it's just 1/2 L. Does that make sense? So then at that point, all you have to do is plug these values in right here. As you can see, we got D, 1/2 L. We got I, 1/3 ML squared. And this M, I made it big because that's how the formula has it, but it's the same mass as this mass, obviously. So once you plug all that stuff in, you really just have to solve it out and solve for T. Physical pendulums, at most, one question on that on the test maybe, if any. Just thought I'd draw attention to it. So in case there is a question, you're not completely caught off guard as to what a physical pendulum is. So then, when is acceleration the highest? So this right here, conceptual questions that you're almost guaranteed to be tested on. When is the acceleration the highest? So go ahead and somebody answer that one. Good, at either amplitude, so you have a wave, right? So at the highest point and the lowest point, acceleration is highest. Or that's my fault, it's the opposite. So acceleration is highest at these points. This one will be positive, this one will be negative. And then for part B, or for 38, when is velocity the highest? At equilibrium, right? So right here and here, you get negative Vmax. And here you get, bless you, here you get positive Vmax. And I didn't ask this one, but where is your net force the highest? Maybe what? Yeah, at either amplitude. So A max and negative F max and A max and F max. So as we've seen throughout this whole semester, acceleration and force are essentially very closely intertwined, yeah.
How come at the top the acceleration is negative? Could you explain that?
Yeah, good question. So why is the acceleration negative at the top? It's because right when it gets up here, it wants to go down, right? It wants to go in the negative direction, and so the acceleration is negative to take it in the negative direction. So yeah, I think that's about all of those. Any questions about those? Cool.
Can we talk about the energy?
The energy, oh yeah, okay, good question. So kinetic and potential energies. So in this case, you'd have your highest kinetic energy where you have your highest velocity, right? Because kinetic energy is velocity. So this right here is also kinetic energy. So I'm just cramming a bunch of things in there. I'll put it more neat on the actual posted version. And so the potential energy would be highest where there is no kinetic energy, which would be at the ends where velocity is 0. So potential energy right there. Yeah. All right, so any questions about that? All right, so and then this one right here is also a conceptual one. What is the restoring force of a pendulum that is 9 degrees to the right of the equilibrium point? So we have a pendulum that looks like this, and it is 9 degrees to the right. So does anyone know the formula for that? So in this case, it would be mg sine theta, right? So in this problem, I'll try to, on the answer sheet, I'll fix that. I didn't give a mass, right? So I just saw that I did not give a mass, so you can't solve it. But the equation still stands. It's the same. So this right here should be mg sine theta. And since the angle is 9, what can we do with this sine theta? What do we do? Yeah, exactly. So it's the approximate angle. So it's small angles, right? So any angle less than 10 degrees, you can change it to mg theta, right? Or not change it to mg theta, but sine theta is going to be essentially the same as just theta. So for example, sine of angle x is just going to essentially give you x as the answer. The thing, though, that I want to make a big note of is angle has to be in radian. So you don't want to make this mistake on your test and do degrees. So don't do like mg times 9, because that's going to give you a completely wrong answer. So you'd want to do mg times whatever the radian version of 9 degrees is, right? So that's all you'd have to do. Mass times gravity times that, only up to 10 degrees. Anything past 10 degrees doesn't work, yeah. Yeah, if you use the sine theta, you can keep the 9, yeah.
So what's the appropriate time to use a radian?
So good question. So you can do mg sine of 9, right? Or you can do, and as long as you're in degrees, if your calculator is in degrees. If your calculator is in radians, you have to convert 9 to radians and do mg sine of whatever that is, right? And if you do that, you don't even have to do sine. You would just do mg times whatever that is. So that's just make sure you're if you're using a degree, be in degrees. If you're using radian, be in radian, and you'll always be right. You can just, that's what I like to do. Yeah, it's kind of pointless. Yeah, yeah. It's just the whole point of the approximate small angles. But you can always do mg sine theta. Yes, as long as your calculator is in degrees. Yeah. Yep. And then last couple questions, where is the only kinetic energy? Where is there just kinetic energy? Good, good. And then this last one, where is there both kinetic and potential energy? Anyone know that one? It's what? It's kind of not, the answer is not even there, right? So where's there both kinetic and potential energy is between the amplitude and the equilibrium. All right, between amplitude, I was just excited to be done with the review. I got a little excited there. So between amplitude and equilibrium is where you have both. So yeah, I mean, I believe that's about all the time we have right now. So I appreciate you guys coming. Make sure you filled out that survey. Just try not to take it with you. Leave it there if you want to bring it up to me before you leave. I'm here for another like 2 minutes. Any like last minute questions I can answer? Anybody? Thank you. I appreciate it. Cool. So yeah, I mean, thank you guys for coming. Good luck on your test. It's next Tuesday.